Hello teammates, it's Mr. Nanini coming to you from the physics bunker. You're going to be watching this on the 23rd, and my intent is to do it like this to give you some practice for the AP exam. A couple things change in our strategy. What I've said before it was changed is when you get the free response part of the assessment, read through all the questions first, answer the ones you're most comfortable with. That strategy isn't going to work because you're going to get these questions one at a time, so you're not going to have the opportunity to look at one and then say, okay, this one I'm going to do first. So it is what it is. Here's what I'd say though to that is when you get your free response question, read the entire question first. Let your mind digest that. And before you start writing anything, develop a strategy. Ask yourself, what principles are involved? What am I asked to do? And how am I going to demonstrate that? If you just start writing, you might get through it. But odds are what happens, you're going to find that maybe your strategy doesn't get you to the end. Maybe you could have calculated something earlier that's going to help you finish it. The other thing is, by just pausing for a little bit in identifying your strategy, you're going to let your brain have time to work. And if you just dive in, that cortisol is going to flow and you're in survival mode. So just take a minute, read through, and you've already done that. So I think it's a pretty good assumption that when you face an FRQ, you're not going to have just one topic. I think they're going to combine topics. And in this case, you got three topics, don't you? You've got some conservation of energy. You've got some two-dimensional motion, free fall, and you've got some conservation of momentum. So you got three topics all in this one. And you're ready, and I hope you realize that. And I'll give you some tips. Teammates, as you do these, what I don't want you to do is say, okay, if I can do this, I'm ready. I'm not going to give you a softball. That doesn't make any sense. I know a lot of your other instructors really kind of massage your egos a little bit and make you feel good. That's just wasting time, though. So this one, I think you did okay. I bet. But just know, don't take yourself through that self-torture. If I can do this, I know what I'm doing. We're still training. It's good. So strategy, we got some conservation of energy. We got like it's a greater angle of pendulum, but energy is conserved. So gravitational potential there is transferred kinetic. Ball's gonna be in free fall, horizontal launch angle, and then we're gonna determine conservation of momentum. So let me take you through my solution, and hopefully this is okay. And if you'd rather me screencast this, or I think I want to do a video of some kind because it helps me make a point. I would write. Now they're not going to score you on this. If they just see the equation, they're going to know what you're talking about. For your own edification, I'd write, I'm going to use conservation of energy. Gravitational potential equals kinetic. Start there, just like we've done in the classroom. Then put in your variables. And that's 1 point. Just for identifying this as a conservation of energy, that's 1 point right there. Easy money. Identify your change in H. You can write that out. You could, right? You know that you got that. Oops, I should have had my straight edge in this, and you know that, and you know this, and that's going to be your change in Y or change in H. Right? You can do that. But you also know your change in H, I should have put a delta, is your length equals L cosine theta, right? You want this side minus that whole length is going to be your change in H. How can you check that? If you get a distance larger than your L, You did it wrong. So you're gonna solve. There's a lot of calculations in this one, and that's okay. You're gonna calculate a height of 0.3 meters. Then we want to determine the speed of the ball. When it hits, that's what the task is, and you're gonna again start with your variables. mgh equals 1/2 mv squared. We don't need those thinking messes. Solve for v, 2.44 meters per second. 2 decimal places is fine. And I'm using 10 meters second. When you get the assessment, and if it says 9.8, 9.8. If it says 10, it's 10. So we cool. 2 decimal places. 1, 2, 3 points. You are on your way. Be detailed. Show where everything comes from. Part B. Calculate the speed of the ball immediately after the collision. Now it's a free fall. It's a free fall problem. I'm going to look here. Horizontal launch angle. Velocity is constant. Velocity by change in x, change in time. I'm going to determine my change in time first. Just identifying how we're going to get velocity. That's 1 point. Determine change in time. You're going to use your old kinematic equation, bud. I'd write the whole thing. Initial velocity is 0. Cross it out. I'm going to use g there. When you're in free fall, I go back and forth on that. I'm going to use g there, so we know it doesn't matter. If you put a, you're good. Change of y equals. Solve for t. T is going to give you 0.49 seconds. How to check that? A 1.2 meter high table. Yeah, sure. What at 1.2 meter high table? It's a bit higher than in the classroom, but you know that's not going to be 3 seconds, and you know that's not going to be 0.1 second. So check your answer. Then so that's 1 point to get time. Teammates, time just can't mysteriously appear out of the top of your head. You gotta show everything you are using. Velocity, changing position time, you got it 2.86 meters per second. 3 more points. Teammates, count them. 6 points already. 6 points already. Page 2. We want to determine the speed of the ball immediately after the collision. Now, this is interesting. It's a conservation of momentum, right? That word collision is inviting you to look at a conservation of momentum. Teammates, write your momentum conservation equation. Start right there, right? For a collision that the objects don't stick together. And recall, an elastic collision, kinetic energy is conserved. Inelastic, kinetic energy not conserved. Special case of inelastic, totally inelastic when the objects stick together. So just because they stick together, that doesn't make it inelastic in and of itself. It's that conservation of energy. So start there. You want to identify the different objects you have. So I'm just going to use the masses. So the mass of the 0.66, the velocity of the 0.66, etc. You want to solve for your final velocity of your 0.66 mass. You're going to rearrange the equation. You are going to subtract this from both sides. Divide both sides by that. Leaves this. Write your equation. Teammates, check it out. 1 point for showing your conservation momentum equation. 1 point for isolating your variable. 1 point for solving. How sweet it is. You're going to solve 1.47 meters per second. 2 decimal places. Again, check your answer. If you got 147 meters per second, odds are a little pendulum in the lab is not going to be 147 meters per second. So just check your answer. What? D, easy money. This one is just a check. Usually you're going to have to justify why. D, indicate the direction of motion. You came up with a positive number here. On the AP exam, in physics in general, the x direction to the right is generally considered to be positive. So I could have put my directions up there. But because this is positive, you know it's going to move to the right. E, calculate the height to which the ball rises. Conservation of energy problem again. You don't have to calculate anything with the pendulum. Again, kinetic equals gravitational. Kinetic equals gravitational. Isolate your variable and solve. That's 1 point. That's 1 point. Is the collision elastic? So I think that's smart to do. I think to state for the reader, you know what an elastic collision is. You're going to say, hey, Mr. Reader Man, or Mrs. Reader Lady, to be elastic, kinetic energy is conserved. You're going to calculate your kinetic energy before the collision. Only one object is moving. You only got to worry about one. The second object was at rest. You've got your mass, your velocity, 1.96 joules. Your kinetic energy after the collision, kinetic energy of the 0.66 kilogram mass, kinetic energy of the 0.22 kilogram mass. Add those together, 1.61 joules. Those numbers don't look the same to me. Kinetic energy is not conserved. Right? Drop the Ticonderoga. So you're not going to have to wrestle. These are going to be far enough apart. You're not going to have one like 1.96 and 1.95, and you've got to figure out are they different or not. There's going to be a discernible gap between. All right. So I think you should feel kind of good about this. I think, and if not, you brought back a lot of neurons. I think if you were to face a problem like this, you would be very well prepared. And I'll talk to you tomorrow. Thanks, teammates.